So people in the room and also join us online. So today it's our honor to have Jim Whiteley from AtkinsRéalis and coming to Exeter to share his work on this Powderham Bank improvement project with us. Jim is an experienced geophysical hydraulics expert and with 15 more years experience. Yes. So it's our honor to having him to talk to us today about this wonderful program in the way it's close to Exeter. Thank you.
Thanks very much. Hoping everyone can hear me online. So yeah, my name is Jim Whiteley. As Albert has already said, I'm the Engineering Geophysics Lead for AtkinsRéalis. So I work in the Ground Engineering and Tunnelling Division with AtkinsRéalis. AtkinsRéalis, for those that don't know, is a multinational engineering service consultancy. But you do have a visiting professor, Oliver Greason, at the Centre for Water Systems, so hopefully some of you have heard of the company through his involvement here. I'm going to talk to you today about a project that's local to the university, actually. So although we are a multinational company, and although I work on projects all over the UK and overseas, this is one that's just down the road from both where I live and also from the university here. So Powderham Banks in the Exe Estuary. I'm going to be talking about how we've used non-intrusive methods of geophysics and drone data to better understand the deterioration of this embankment, and how we can use that data to manage it for the long term. Before I get into the project, what I'll do is I'll give a brief overview of what I mean by geophysics, the sorts of techniques we use, how they work, some of the uncertainties we encounter with them, why we use them on geotechnical projects, and then I'll go into a bit more detail about the project itself and what we're doing on the Exe Estuary. I always like to start my presentations with this slide. Particularly in the engineering world and geotechnics, there's a very big interest at the moment in 3D geoscience. And most of that comes from drones. So a lot of it is around this idea that we can get very high resolution surface imagery and information from things like drones and satellites. And many people tend to see this as extremely innovative. And really this slide is me making the case that we've been doing lots of this for a long time, particularly in the sphere of remote sensing. And when I have lots of conversations at work with people about geophysics, they also tend to think this is something that's really innovative. And what I'm trying to make people understand here is this is also something we've been doing for a long, long time. I always like to tell people that I don't see geophysics as particularly innovative. We can do innovative things with it, but the actual application of geophysical measurements is not something that is new. We've been doing it for a long time. So at the top here is a sort of a potted history, as it were, of the history of remote sensing. So going back to this first image on the top left, this is an image from the New York Public Library from the 1870s, taken from a hot air balloon. It's a stereoscopic image, which means if we have a stereoscope, we can look at this surface in 3 dimensions, which means we've been using 3-dimensional surface imagery as far back as the 1870s, well over 100 years, something that's not particularly new to us. We saw big developments in the application of surface imagery throughout the early 1900s, particularly in the interwar periods when we started to require high-resolution images of the surface in the UK. And then, of course, the launch of satellites, Spot and so forth in the 1980s that allowed us to have global digital elevation models. And then really quite recently we've seen innovation in drones, which has allowed us to have this bespoke information at the site level around topographic imagery, multi-spectral data and other sorts of derivatives, some of which I'll talk to you about today. And as I said, often when I talk about innovation in meetings, it sparks up several feelings when I'm talking to clients. So I think in the research sphere, it's quite well understood that if you take money and turn that into research, we call that research. If we take research and turn it into money, that's innovation. And in consultancy, it means something slightly different. It normally means cutting edge. It means interesting, new, can mean risky, can mean something that people are a little bit averse to because they don't think it's tried and tested. And so again, what I'm here to say with geophysics is that it's not new. We've been doing it for a long time, and we can do interesting things with it. So as far back as the 1910s, we had the Schlumberger brothers who were applying electrical resistivity methods to the ground to better understand what the ground beneath our feet is doing. And I recently was alerted to this paper from 1939 in New Zealand, where seismic and magnetic methods, which are both geophysical measurements, were used in the investigation of a dam being built. So we've been using geophysics in the engineering and geotechnical sphere as far back as the 1930s. It was in the 1990s, though, where we started to see major developments in how we could take that data and model it. So this is when the first software was released that allowed us to do modelling on home PCs and equivalents, which meant we could be in the field and actually look at data, which allowed us to be much more flexible in how we interpret and use the data. And very quickly, we advanced from having that processing capability in 2 dimensions to 3 dimensions, and then in recent years, 4 dimensions. So how we can get time-lapse images of the subsurface using these multi-dimensional approaches. And that's what I'll be talking to you about today later on, is the application of four-dimensional imaging to this flood defence down in Powderham Banks. So the other thing with this as well is making this point that, when I talk to people about 3D geoscience data, everyone has a very big interest in the surface. They want to see the DTMs, they want to get the drones out on site. And my question is always, well, as engineers, aren't we more interested about what's going on beneath our feet? And really, we should be using more of these geophysical techniques to try and understand what's going on beneath our feet for the cause of geotechnical engineering. So, as I said, part one, we're going to make the case for geophysics, why we should be using it in geotechnics, how we currently use it, what we're doing right, what we're doing wrong, where we can improve. And the typical application of geophysics in the geotechnical engineering sphere is in ground investigation. So where we have a site, like you can see on the screen there, where we know nothing about the ground, and we want to try and understand what the potential risks might be when we're trying to design or construct something on that site. Now, traditionally, and more commonly, we tend to go in with an intrusive ground investigation, so we'll go and do some drilling, spend some money on that, and we'll then move to a new position where we'll go and do more drilling and find something different. And of course, at this point, we start opening up questions about the ground. What's the difference between those two locations? What's causing that? Is it geological? Is it anthropogenic? What can we do to better understand it? But normally, the typical approach is to keep drilling until we've run out of money, and then we have to make some sort of interpretation of the ground conditions. And we do that using our expert judgment. We come up with a ground model. And what I always say is, at this point, we need to ask ourselves two questions. Have we fully characterized the ground? Do we really understand everything that's going on within the ground subsurface? And by doing that, have we minimized the risk to the design or the construction of whatever it is we're trying to achieve on the site? And my contention is that if we're just relying on intrusive ground methods, where we're drawing these fuzzy and uncertain lines between known pieces of information, that we haven't achieved those two goals. So we could be using a different approach, and this is becoming more common, which is to use geophysical and non-intrusive investigation methods. So this time we're going to take some of that budget and allocate it to a non-intrusive ground investigation. So here is a typical resistivity system. This is the main technique I'm going to talk to you about today. I won't be going through a list of all the geophysical techniques and how we use them in different scenarios. If you do want any more information on that, there's some really good guidance that was released by Syria a couple of years ago, which can explain that in more detail. Or if you want to contact me after, I'm very happy to answer any questions you might have. But in the setup you can see on the screen here, what we've got is a series of electrodes that have been placed for equidistant measurements across the ground, connected to a resistivity meter that you can see in the ground there. We're going to inject an electrical current between pairs of electrodes and measure the arising potential voltage across another pair of electrodes, and we'll do that for all the different combinations of electrodes across that array. And in doing so, we'll make up a two-dimensional, in this case, picture of the subsurface and its distribution of resistivity. The further apart those electrodes are, the deeper into the ground we'll see, but there'll be a less resolution, and the closer they are together, the higher resolution, but the more near surface. So we always have this trade-off between how deep we want to measure and the resolution of the model we're going to get. So back to our ground investigation, we've set up our instrument, and now we've spent half the budget on trying to get this picture of the ground. Now, the picture we get of the ground is not certain. There's lots of uncertainties in the data, and what we get is this really, both literally and scientifically, fuzzy picture of what's going on. But it gives us some idea of the sorts of things that we might see in the ground, where we can then target with our intrusive investigation, where we can then allocate our resources to better understand and truth the information we have. So we spent half our budget on doing the geophysics. We can spend the remaining half then on drilling that and getting the certain information that can either prove or disprove the model we've got from the geophysical investigation. And now when we ask ourselves that question, is the ground characterized? Well, now we have some information from everywhere. We haven't got any blind spots in the data. We can see everything that's going on the ground. And therefore, are the risks to design minimized? Well, yes, we've got some understanding of everywhere across the site. We prove that it works with intrusive investigation. We have much more certainty on the knowledge we're getting from that investigation of the ground. So, I've told you why we use geophysics, and I'll briefly touch on what is geophysics. I mean, the main benefits are that it's non-intrusive, so we don't have to dig anything up. We may put electrodes into the ground, maybe 20 centimeters in, or perhaps geophones put onto the ground surface that, again, are sitting on a spike. But we don't fundamentally have to remove any ground, we don't have to drill or put anything in there to be able to get these measurements. And consequently, because we are using these spatially extensive methods, it's relatively inexpensive. When you think about the volume of data we get for the amount of effort that we spend, we can get a lot of information without having to go and dig things up, which makes it much cheaper. And the other large advantage is it's multi-dimensional. So whereas our intrusive ground investigation methods, like boreholes or trial pits, are typically one-dimensional, they're just telling us about one piece of information in the ground, we can extend these investigations using geophysics to be two-dimensional, three-dimensional, as I said earlier, four-dimensional, where we're including a time-lapse element as well. On the top right there, you can see the sort of definition of geophysical surveys, and it's using these measurements of signals, and signals in this case can be active signals. It can be things like seismic sources we generated with hammers, or in the case of the resistivity instrument, an electrical current we're injecting into the ground. Or it can be passive. We can be measuring the Earth's gravitational field or magnetic field. But fundamentally, we're picking up some physical property that is then telling us about what's going on in the ground surface. So those are the main benefits. And then this is the bit where I have to show you the long list of limitations, which is always a bit disappointing. But the main limitations are that we have limitations on depth of investigation. So as I said, we tend to be able to see things in the near surface with much higher resolution than those that happen in the deep surface. And we also have to have this measurable contrast of property as well. So if we're trying to, for example, use gravity to look for a density variation in the ground, there must be a change in that density for us to be able to detect it. A classic example is if we have a mine shaft which is air-filled, the density contrast between that and the host rock around it is extremely high, so we have a very good chance of detecting it. If, for example, that mine shaft is filled with rubble which has a similar density to the rock, we're not going to have a very good chance of finding that. So measurable contrast is really important for these techniques. The other thing then is that when we have actually acquired that data, the signal that we've measured and modelled is rarely a direct measurement of the thing we actually want to know in the ground. So a good example of this would be using a magnetometry survey to look for example, some buried tanks. That magnetometry device is going to pick up ferrous metal in the ground. It doesn't necessarily mean that ferrous metal is going to be the buried tank we're looking for. It could just be another piece of metal which has a similar dimension and magnetic intensity to the buried tank. So we have to always have this understanding of uncertainty, what it is in terms of the properties that we are looking at. And coupled with that is then the fact that geophysical measurements can be sensitive to more than one property in the ground. So again, the classic example of this would be a resistivity survey. Resistivity is affected by the amount of clay in the ground, which conducts more electricity, so that tends to make the measurements very low resistivity. But water does a similar thing as well. So we get low resistivity measurements where we both have clay and water. Where we have high porosity rocks, or perhaps gravel, or perhaps some sort of fresh contamination, we can see very high resistivity results. And therefore, we have conflicting signals that can drive what the spatial distribution of resistivity is. And we have to try and disentangle those. The way we normally do that is to use multiple methods so that we can look at different measurements of these physical properties and try and reduce the uncertainties in a co-interpretation of all of them. And then finally, and I think the thing that we don't talk about very much is that because we are going out in the field and collecting data and we're taking it back and we're applying a modelling process, there are many, many stages at which errors can be introduced, which can be either in the acquisition of the data in the field, it can be in the filtering and processing of that data, the inversion and modelling, which I'll touch on in a second. But it's really important we have qualified and trained people with experience to be able to undertake these. It's a very precise science that's applied in a very messy environment, which is the real world. And it works fantastically when we have the right constraints and expertise to do it, and it can be really seriously misused if we don't have the right people who are able to understand what's going on. I think the last point then, which is one that particularly applies to things like resistivity surveying and things like seismic, is that we're not always, the data that we're getting is not the final model we're looking at. So we have to go through this process of what's called data inversion. So that is effectively taking the information we've got and trying to find the ground model that fits that distribution of data. And the best way that I can describe this is, many of you might remember from primary school, you've got a piece of paper with a bar magnet underneath and then sprinkle some iron filings on top, and you'll see how the iron filings match the magnetic field around the bar magnet. Well, in a forward modeling problem, we would know the size of the magnet, we would know how magnetically intense it is, and if we have that information, we can forward model the magnetic field to quite a high degree of precision. But that's not the case with geophysics. What we have is the magnetic field, and we know nothing about the bar magnet. So the bar magnet could be very small, very highly intensely magnetized, or it could be very large, and it could be very weakly magnetized, and it would give a very similar magnetic field. And that's what's called an ill-posed problem, which has a non-unique solution. So we have to find the ground model that fits that data the best, and that means we have to look at things like fitting criteria, RMS errors, chi-squared fits, to make sure that what we have is something that is reasonable from a mathematical point of view, but then also something that fits the ground with our understanding geotechnically and geologically with what's going on in the subsurface. So it's a very complicated process getting from field data through to a final model that actually tells us something useful about the ground. And fundamentally, it's all wrapped up in this quote, which everyone's probably heard some version of, which is that all models are wrong, but some are useful. And that applies to most things in the ground. It doesn't matter whether you're creating a ground model from a series of boreholes where you have to interpolate the data in between, or whether you have geophysical data, which is everywhere but slightly uncertain. There are going to be errors and assumptions made in those models, and we need to understand where they are. And when we understand where they are, we can get the most out of the model we're working with. So that was a whistle-stop tour of the principles of geophysics, where we use it, how its role is in geotechnics. And now I want to talk to you about the actual project we're working on with the Environment Agency and the British Geological Survey down at Powderham Banks, where we're putting some of those principles into practice. And this is actually, I've just spent a couple of minutes on this slide because it's actually the best photo I have of the site. So we're looking at, we're facing south here, we've got the Exe Estuary, which is flowing out towards Exmouth and Dawlish down at the far reach of the photo here. And the flood defence we're interested in is this section you can see along here. So this is the Powderham Banks flood defence, which was constructed about 200 years ago. And you may be able to see that there's a footpath on top here, which is used by many avid bird watchers because the area's got a lot of interesting wildlife. And there's also then this cycle path as well. I think about 80,000 people use the cycle path every year to get to the city of Exeter on their regular commutes. And this path forms part of the Exe Estuary Trail, which is also used by about 150,000 people recreationally to cycle to and from Topsham down to Exmouth and back up from Dawlish to Exminster. You'll notice that we've got this railway here. So this is the mainline railway that connects Paddington to Penzance, so a critical piece of infrastructure for the southwest. I always think it's quite funny that we've got millions of pounds being spent down in Dawlish on the protection of this railway, and yet we have a 200-year-old flood defence which has not got a lot of cash injection, which is protecting the exact same piece of infrastructure just miles up from that particular location. Interestingly, this pond down here is protected. Brunel built one of his steam houses down here, so there's an abandoned building from Brunel. And then the area which you can see here, the sort of wetland behind the embankment, is also a triple SI Ramsar site as well. So there are lots of potential sort of elements of risk here for flooding, which we want to try and protect through the use of this embankment. Now, those of you coming from a geotechnical background or an asset management background probably don't need me to tell you that in the UK we're facing something of a crisis when it comes to long linear infrastructure at the moment. We have increasing deterioration of failure rates, which is partly driven by the fact that much of our infrastructure is extremely old. Victorians are extremely good at building infrastructure to last, and it's lasted way beyond any kind of design life that it ever had intended. But increasing pressures from climate change and the fact that this infrastructure is getting old is causing it to fail more often. And we're also having the pressure on having reduced budgets, better ways of managing this infrastructure, which is causing it to become a bigger problem. And the other thing I want to mention this as well is that when I'm going to be exclusively talking about flood embankments, although most of what I could be talking about here today would apply to rail assets and road assets as well. With flood embankments particularly, much of the problems that we see that precipitate the deterioration and catastrophic breaches that we want to prevent, they occur inside the flood defence itself. So where we have internal erosion, that's a process that's taking place inside the flood embankment that we can't easily see through visual inspection alone. Hopefully this is a concept that many people have come across before, but this is the idea. We have something called a performance curve or a deterioration curve for assets. In the sort of lower end on the x-axis here, we can see we've got new assets that have been built. So these would be things like your HS2 embankments, which are in a phase of bedding in. They're reaching their design performance. And then after they've reached that, there's hopefully a long period of reliability, which lasts for the same amount of time as the design life that we intended to build that asset with. But there will always become a point where we go into a state of deterioration and decline. And what we're really interested in is catching that deterioration before it becomes unreliable. And the transition from something being in a state of deterioration to being unreliable is normally punctuated by some sort of failure. So in the case of a flood defence, that might be internal erosion and a breach of the asset with water moving from the place where we want it to stay to somewhere we don't want it to be. And the reason that's important, the point of failure, is because if we can do things before that point in time, normally those interventions are cheaper, they're less intrusive, and they can keep the asset going for longer without having to get into a failure state. But if we're having to fix problems that are failures, we've got to repair breaches and embankments, that's intrusive, it's very expensive. And in the case of something like Powderham Banks, it means we have to do things like close footpaths and cycleways, which so it brings a lot of disruption to the area as well. So what we want to do when we have non-intrusive data is basically try and see inside these assets without having to dig anything up, which is far less intrusive, to try and spot where these problems might be well before we get to that point of failure, so that we can implement these non-intrusive early repairs that hopefully keep the asset going for longer and keep it in that reliable state. So to do that, what we're trying to really say is we're using these techniques to try and work out which sections are vulnerable to failure, where do we have the evidence that shows us we may have the potential for future failure, and can we proactively prevent that by fixing those and then continuing to monitor them to see that they are that those repairs are doing their job. So I spoke a bit on the panoramic slide, but the actual section of the Powderham Banks that we're interested in runs from the Turf Hotel in the north here down to a railway bridge which crosses the railway just in the south-east here. To the north-west, we've got the village of Exminster, and there's about 100 homes there which are also protected by this flood defence. As I mentioned, we've got the mainline railway and also the Triple SI Ramsar wetland site sitting behind it as well. Because the asset was built about 200 years ago, there's no modern design construction in the construction of the asset whatsoever. It's basically made from dredged up alluvial silts, which were put into a very rough trapezoidal shape. And it wasn't until the 1960s that there was a major upgrade to the embankment, which comprised the installation of this revetment, which is a stone and pitch revetment at the front here, a wave return wall, which also has a footing underneath this footpath, and then some regrading of the back face as well. The Environment Agency currently spends about £100,000 a year on maintenance, and up until recently that maintenance schedule has been driven by visual inspection. And I think it's fair to say I'm not an expert in asset inspection, but if I had to come along to this embankment and try and pick out where the deteriorated states are, I would probably say most of this embankment needs to be fixed, because you can see below the mean water line here, we've got a lot of missing pitch between these blocks. In other sections, as you'll see later, we've got areas which have got no block work on where the core is completely exposed. We can see at the wave return wall here, we've got offsets, there's opening up of cracks along the top here, which is obviously a means for water ingress to get in. So it's a very difficult asset to manage because of its age, and because, not just because of the age of construction, but also because that repair and the upgrade in the 1960s is itself now being in position for 70 years or so. The records of inspection going back in time are not particularly great. There's certainly a very few digital archives with regards to which bits have been repaired and which bits have been inspected in the past, and really we have some of those since about 2022, but going back further than that, most of it is anecdotal rather than being recorded. And currently the EA is exploring options for replacement of this existing embankment on the site. So there has been intrusive investigation of the site in the past. In 2013, there were 6 cone penetration tests undertaken along the site, and also 2 direct push logs as well. So we have logs for those locations. And the CPT results generally show that we have very low cone resistance, so less than 5 megapascals, and very low pore pressures in the embankment as well. When we look at the actual logs, we can see that we've got basically 3.5 metres of made ground, which is the alluvial sediment that was put in place, and that has been deposited or built straight onto an organic layer, which is probably the old wetland environment that was there previous to the construction. There's no subsurface engineering that's gone into the foundation of the structure. It really is just lots of alluvial sediment built up on top of natural wetlands. And that means that as well as movement of water potential through the embankment, we also get lots of water underneath the embankment as well, although that is of less of concern. As I said, last major update was in the 1960s, and this is just a schematic showing that stone pitching on the estuary side, the footing there of the wave return wall underneath, the footpath, and then the regrading on the back face as well. And as I said, the last inspection that we had prior to our involvement with the project was in 2022, and we can see from these photographs, there's very clear evidence of lots of deterioration of this of the revetment. So where we have lots of stonework that's been removed sitting at the base of the slope, and that's captured quite nicely in these photographs. But what is interesting is that this inspection was done in 2022, and it was only a year later that we had quite a major breach of the embankment that took place. And this opened up on the footpath. It was a hole that went down about 2 metres into the embankment. This was alerted by a member of the public who saw this and called the Environment Agency. And there was no indication in that previous inspection report that this location was one that was going to fail in this manner. At the time of this failure, the water level in the estuary was half a metre higher than the track of the railway. So had it progressed to a catastrophic breach, we would have seen inundation of that railway and water lapping up against the embankment, which would have been very difficult to manage. And the figure I've been given for the fines that we put in place for closure of the railway run into the £1,000 to £2,000 for every minute. So it's a significant financial risk if this thing is to breach and cause flood inundation of wetlands. And this location of the breach is only 50 metres away from the railway as well, so very close to that vulnerable element of risk. So the question that was tasked to us was, well, how do we find where there may be other areas that have this potential for failing as well? And obviously, in my first slides that I gave, I showed that we could go on an intrusive investigation campaign, but if we are showing in the sort of history that we have that we don't have a good correlation between where we have deteriorations visible and the potential for breach. Where do we even start to target to do those intrusive investigations? So we proposed a kind of rapid, non-intrusive, drone-based and geophysical-based survey, and using several types of techniques to try and understand what was going on with the embankment. So from the drone side of things, we're using high-resolution imagery, and we can use that then using structure from motion to get topography of the embankment in good resolution as well. Multi-spectral data, so this is data that's beyond the visible red, green, blue spectrum that we all see, and also thermal information about the surface temperature of the embankment, so we can look to see where there might be water that's causing a change in temperature. From the geophysics side of things, we're then looking at resistivity measurements, so the same setup essentially that I showed you in the opening slides, where we're injecting currents to try and reconstruct an image of the resistivity distribution. And that's quite crucial because we know we have saline water ingress, and saline is going to change how that resistivity is picked up. It's going to make very low resistivity because saline water conducts electricity really well. We also have an electromagnetic survey, so this was just done on the footpath and on the embankment. Electromagnetics give you a measurement of conductivity, which is the inverse of resistivity. It's just from a much shallower position on the ground, so it complements our resistivity measurements. And then we also had a ground penetrating radar survey as well, which was looking for these discontinuities within the embankment structure that may be indicative of water or other sorts of features related to the mechanical properties of the ground. The topographic surveys that we had done initially were undertaken by Lewis Brown, who are a local contractor. Drone surveys were done by AtkinsRéalis in-house, and we had Zetica, who were a geophysical contractor to come in and do the geophysical surveys. And those works were undertaken in August 2023, so a few months after that initial breach. The breach was repaired very, very quickly with a temporary repair. The surveys were undertaken in August, and then it was September 2024 when the permanent repair was taking place. So the surveys were done before the permanent fix was made to that breach zone. This is just a photo showing what those drone surveys look like. So we have a multi-copter that is carrying the sensors that we're using to pick up that data. As I said, high-resolution imagery, multi-spectral data. The data set we're really interested in for multi-spectral is something called the Normalized Differential Vegetation Index, and that gives us an idea where we have different cover types on the ground, so we can very quickly classify the types of ground cover that we see, and also the thermal data to look for areas of leakage as well. For the geophysical side, I mentioned the 3D electrical resistivity tomography. So what you can see on the right hand of the image here is where we put out these lines of electrodes along the entire 1.6 kilometers of the embankment. What we actually did was acquire those separately, and then we asked the contractor to process that as one three-dimensional data set at the end. So we had a continuous three-dimensional data set, 1.6 kilometers of the embankment. And then, as I said, the electromagnetic surveys and ground penetrating radar surveys that took place on the footpath and the cycle path. And what we can do with that is we can then bring it into this three-dimensional environment. So what you're seeing on the screen now is a topographic image created from those structure from motion photographs. There's a bit of vertical exaggeration on there. We can then drape the optical imagery onto that. I should say this has been down sampled for the purpose of the video. We can then also bring in things like the thermal imagery as well, so we can see really clearly that the footpath there has got this very different heat signature to the rest of the embankment. And also we can look at that NDVI, the Normalized Differential Vegetation Index, which tells us about the different cover on the ground. So this is now a bit more of a subtle indication of where we have differences in the surface. And that's a really nice way of digitizing and capturing all the information from the surface, but of course we want to know about what's going on inside the embankment as well. And so that's where we looked at the geophysics. We have the 3D electrical resistivity tomography survey. So this is the entire extent, looking down way beneath the embankment. But really we're just interested in that top 3 meters, so we can trim the rest of that bottom data off and start to look for where we have these low resistivity zones that may indicate where we've got saline coming through the embankment. When we put that all together, we can start trying to see patterns and things that are changing. So we have here this very clear red hotspot in the NDVI. And when we look at the optical imagery, we can see that we've got very clear missing blockwork here. And then when we start to look at the geophysical data, we can see that sitting just behind this, we've got this cluster of low resistivity cells here, which have just been coloured purple to make them really obvious, which is indicating that we have known damage and a potential pathway for water getting through to the other side of the embankment. When we start to look along, we can see that these hotspots actually occur quite nicely, where we have all sorts of manner of missing blockwork. And again, areas that we tend to have missing blockwork, we have these occurrences of these low resistivity anomalies, which are indicative of potential for saline intrusion through the ground. The red lines you can see on the screen there is just some additional information from the ground penetrating radar survey, so we can use that to also then add more lines of evidence into our interpretation. And moving up through the embankment, we can then see that as we get to the area that breached in March 2023, there's still, because we haven't had the full repair at this point, low resistivity apparent in that location. And actually there's several areas around here where we've got these low resistivity channels that seem to be making their way through the generally high resistivity embankment. And that's something that we see as we then start to work our way up through the sections as well. So having these multiple sources of information, being able to bring them into the three-dimensional environment is really key, because this means we can then start looking at all this information together and working out from a holistic standpoint what is going on with the information that we've got. And so, as I said, we have this for the entire asset. We're not limited to having those one-dimensional investigations that we normally get from intrusive investigations. We have lots of information from everywhere. And of course, now the job is to try and work out what the uncertainties are, work out how we can use the different data sets to try and increase our certainty around our interpretation. So the first thing we did is we went out to visit the site, and we picked out about 20 locations which we felt had multiple lines of evidence from the drone and geophysical surveys that suggested there was something going on inside the embankment that could be related to deterioration. And just from going to do the walkover, we visited all 20 and we saw that 16 of those locations had evidence of deterioration in some format, which basically fell into two types. It was either damage to the revetment, so missing blockwork, so sections like this, which are extremely obvious, you don't need a geophysical or drone survey to spot that. But perhaps the more subtle things is where it's very difficult to see on the screen here, but what we have is rafted blockwork. So there is a hollow underneath this blockwork. It looks intact, but actually there's quite a large void sitting underneath that. And we found those at several locations where we picked up the information from the geophysical survey. The other thing we then found was kind of more significant voiding. So here we are at the base of the wave return wall on the estuary side. That tape measure is 70 centimetres underneath the wave return wall. So there's a significant void which is present there, and that was at one of the locations. And again, we could see by getting down into the blockwork that some of these voids were quite extensive, going into the blockwork itself and underneath the embankment. I think the critical thing here is to say that what we're not saying is that we found all the areas of deterioration from the geophysical survey. What we've shown is that the geophysical survey shows us where there are things that are deteriorated, but we know for a fact that there are more than 20 locations along this embankment that are experiencing deterioration. It may just be that these are the more serious ones if they're picking up on a survey. Yes?
Sorry, can I ask you a question?
Yeah, sure.
Like, because sometimes you just like discover this voiding, but is it from this point, like an environment agency gonna think that's really a threat to embankment?
Well,
because some of them can be very small.
Yeah.
I don't know, like how they measure it. What's the matrix of risk, for example?
It's a good question. If that conversation was had, I wasn't part of it, but we'll see what happens next with this information, which will, perhaps answer some of those questions. So it's a really good way of giving us an idea of where to look for what we think might be some of the more serious locations. So the main deliverable then was for us to take those locations, and we graded them. So a group A location, we said there's more lines of evidence from the drone and geophysics here to suggest that we have something more significant, and a group D location is something that is less serious. There's something going on, but it may not be attributable to significant deterioration. What we could also do then was bring in some of those historic observations, so observations from the inspections, also some of the anecdotal evidence as well, the positions of historic breaches, bring it all into a GIS so that we have this map that shows us where things are happening. And immediately, before we've even actually really started to think too much about what this means, we can see some interesting distributions of these things. So perhaps not surprisingly, the areas where you've got these blue stars, which is where we've had indications from past inspections that there's damage to the revetment. That is also where we have quite a significant cluster of these, what we call higher risk anomalies, things that show more lines of evidence. And of course, they're right next to where the channel comes in against the embankment. So the embankment's experiencing more energy from the estuary at these locations, perhaps a high head of water when it's got these spring tides. So that kind of confirms what we might understand deterioration to be, where the channel's the closest, where we've had more historic information, deterioration, we have more current deterioration. But what was interesting is there's some sections where we've got no indications of historic evidence of failure, but we're still picking up some of these anomalies. And these are the ones that we're less certain about, because we don't have that empirical evidence to back it up. For example, on the headland here, we've got quite extensive mud flats which are sitting there, which should break some of the energy from the tides. And up in this section, this is actually on the tributary to the canal, the Exe Canal, which comes off at this location. So it's somewhat sheltered from the influence of the estuary at that location as well. But we can draw some of those large-scale conclusions about which sections, broad sections, might be more vulnerable. Okay, so we delivered that, and we said this is where we think the problems are. This is probably the bit that leads into your question. And we said, over to you, here's the sections, and The survey was done in August 2023. I think that information was delivered towards the end of 2023. By April 2024, the following year, we had our first named storm come through, Storm Pyrrhic, and there was quite a significant amount of damage done to one of the sections of the embankment, which just so happened to be at Exe Estuary, which was up here. So again, not somewhere that the Environment Agency was anticipating there to be damage, because it's not somewhere that has been damaged before, but coincided with a location that we said there was evidence for some structural or deterioration defects in the embankment. Okay, that's one event. That's could be a one-off. That's fine. But by August 2024, again, August not traditionally being a storm month, but a month that is not known for sort of extremely the conditions that would precipitate failure, we had another piping failure at the embankment. So this happened during an astronomical tide, I believe, and we had, again, a failure that happened. This water started egressing through the back of the back face at one of the locations that we found that we deemed as a category A, so poor evidence. And in October last year, we had 4 failures that happened in one weekend. And they all happened, bar one, at locations that we had flagged as having evidence from the geophysical and drone surveys. The one that wasn't, which was this one, we went back and had a look at the data, and actually there was a subtle indication that something was going on there. But I think it's important to remember that 15 months has gone by from when we did the survey to when this failure happened. And this is a dynamic environment, things are always changing inside the embankment. But the key thing here is that if you were to take this embankment, 1.6 kilometres, and split it up into 5-metre sections, you have 320 locations which you would have to pick which one is going to fail next. And if you picked 20 of those and said we think failure is going to happen in 20 of those, and then 5 of those actually go on to fail, you've got a 1 in 3 million chance of getting that right by chance. So the geophysical survey has statistically shown you where these potential problems are going to happen. But the main issue is that's a snapshot. So that's a snapshot from August 2023, and the question is how applicable is that to 6 months, 12 months, 5 years, 10 years down the line? To be able to understand how these things evolve and how they change, we had to look to some form of monitoring. And so that's where the phase 2 of the project came in. So what we did is we worked with the British Geological Survey, and we used their equipment called a prime system, which you can see sitting down at Powderham Banks here. And this is effectively an alternated resistivity meter. So within this cabinet, which is run entirely on solar panel, energy from solar panels, we have a resistivity meter that is connected to a cable. So this cable has got a series of electrodes that are buried into the ground. The cable itself is then sitting within a trench which is buried. And that instrument is collecting the same type of resistivity data we saw in that phase 1, but this time it's collecting it up to 13 times a day. And because we are using electrodes at 2.5 meter space, we actually have 2 systems, so each of them addressing 256 electrodes. So they're actually getting 26 data sets a day. So the single survey we had from August 2023, we're now getting equivalent of that data 26 times a day. I should say that's when the sun's shining and the battery is fully charged. But that system went live just over a year ago, so for just over a year we've been getting this data through from the system. And the main principle here is that, well, I'll show you actually in the next slide. So this is the initial baseline model, and this is effectively the same type of data that we got from our snapshot survey. So what we're seeing is distribution spatially in resistivity, where we've got some of these higher resistivity measurements. We're perhaps looking at areas of the ground which are, so interestingly you can see the new repair there. It's high resistivity because the type 2 material is including the water, which would make it less saline. But we've also got areas which indicate where we have perhaps more gravelly conditions or perhaps the influence of trees. And so from a spatial perspective, we can look at that data, but it doesn't tell us anything about those time processes. I mentioned at the beginning that there are several things that change resistivity. So one of them is clay content. Well, the clay content doesn't change very much over time. Same with porosity, that they're fairly fixed in terms of geological time. But the thing that does change significantly would be the moisture content. If we have water that's entering into the embankment, that changes the resistivity over time. And so what we can do is take the same measurements from the same locations. This time we're looking at effectively the same data set, but changing through time. And the influence of that change in moisture is now driving a change in resistivity that we can confidently attribute to saturation conditions, because we know that the other parameters that affect resistivity are not changing, or at least not changing at the same rate that would concern us. And so now what we can start to see is areas which are changing. And the ones we're particularly interested in, you may see them flash up occasionally in this section, is where we've got these pink cells. And they're the ones that I've highlighted to show where we have a drop in resistivity over time. So that's where we could have saline water which is coming through the embankment, causing that drop in resistivity and indicating where we've got leakage. The fancy coloured blobs which sit along here are just our digitisations of where various repairs have happened, because since we had those the August piping failure and October piping failures, we've had various repairs undertaken by the Environment Agency. What does that look like in practice? So in January 2025, we came back from our Christmas break and we looked in the data and we saw we had these two very clear signals in the inversions which indicated that we had potential for leakage in those locations. Called the Environment Agency, we went down to site the next day, and this was the point where, after walking around for 10 minutes, I thought, oh dear, we can't see anything, my career is in the balance here because this thing isn't showing us any leakage. So we stood at the location where the system said there was leakage, and we were talking about what it could be. And then we realised actually that there was leakage there. So it's very difficult to see on this photograph. The water you can see at the base here is actually just seasonal flooding from the wetland behind. But what we have here is a sort of cone of wet water. My foot is about ½ metre up the embankment. And I should have taken a video, but there's actually a very slow trickle flow coming out of this location. But the key point here is that had this been tried to be detected in a visual inspection, it would have been missed. It was really, really subtle. And the system showed us exactly where we needed to go to try and find that leakage that was happening. So once we know that there's low-level leakage, and low-level leakage not being the leakage we're particularly concerned about, because it's not something that's going to precipitate a significant breach very quickly, we then have options about what we can do to remediate that. So the photograph that we see here, this is an aerial image that was taken after one of the October piping failures, one of the more significant breaches from last year. And there's two things that were done to remediate that. So the first one is the back face here, so the landward side has to be excavated, new material has to be brought in, has to be compacted and reinstated. And the second thing is that we can then apply marine water to the estuary face here, which effectively seals up any gaps that we've got in that marine, in the estuary side face, so preventing the further ingress of water. To do this repair, so the excavation and reinstatement, for every 10 metres is about £125,000. So it's a significant, when you consider that the maintenance budget is £100,000, it's a significant investment to go and fix these things. To do the same length of sealing at the front is £12,500. So it's 10 times cheaper if we can seal the front face without having to go and do any excavations of the existing breaches. And that's what you can see here. So this is October, this is us having to close the footpath, bring in the excavators, so plant on site compounds. This is during a period where we've got overwintering birds. It's quite intrusive, it's not particularly great for people who want to use the cycle path. And it's a couple of days on site to go and fix any issues that we've got. All the alternative is to send down a small crew of people who can then take this marine water. There's no plant on site, we don't have to close footpaths, we can just apply that to the front face and it can keep out the moisture. That's what this system allows us to do, be more proactive, to implement these lower cost and cheaper ways of maintaining the embankment. Crucially, because the monitoring system is still running, we can still look at data. No problem, that's coming down now. We can still look at data from that system to work out whether it is actually keeping the water out, because we still have the system in place, we can still see how that's working over time. What we've got here is the Power BI dashboard that we have in the Atkins office, which is we're able to log in and see in near real time, I think it's with a 24 to 36 hour delay, what the resistivity is doing. We can look at changes in particular cells at particular locations of interest. We've also got, you can see on the right there, we have tidal data, rainfall data, also soil moisture and temperature data as well from a sensor installed on the site. So we can use this to work out if our repairs are being effective in keeping the water out from the embankment. Just to emphasise that point, this was a section of repair that was done after October 2024, so the prime system at this point wasn't in full commission, but it was in its pre-commissioning phase, or commissioning phase I should say, where we were getting data, but it was preliminary data. And the section you can see here, which is green, has been repaired by one of these front-face marine water repairs. There's a section here which is showing a bit of noise, and that's because there's a viewing platform which has got these metal gating baskets, and metal always interferes with the signature of the system. But fundamentally what I'm trying to show is that the area that was repaired here, where we've got these blue colours, that's where we're getting a wetting up of the embankment, and we can see that actually the areas outside of that repair get far wetter far quicker because the water's getting in, whereas across that repaired section we don't see the ingress of water at the same rate or to the same degree. So that's the way that we can monitor those repairs to make sure they're being effective. And that really underpins how we can use this to look at deterioration near real time to make those better management decisions. One of the things that we're doing in addition to using resistivity on the embankment is that we put in a fibre optic cable at the same time. So with fibre optics, we're interested in three potential data sets with that. The first would be strain sensing. So this is using information along the fibre optic cable to see strain in near real time. That could tell us about subsidence or rotation of those wave return walls, areas where we may have impact of sort of longer term processes on the embankment. We can also use distributed acoustic sensing, so this is picking up very small micro tremors and microseismic events, or perhaps using the noise from the trains that are nearby to generate shear wave velocity images. That can tell us about the stiffness of the embankment. And we can also use it to look at distributed temperature sensing as well, so understanding where we may have temperature changes in the ground associated with leakage. And so that cable's there. Unfortunately, we're trying to get some R&D funding off the ground to get the equipment to be able to do that. But having that geomechanical information from strain and acoustic in particular would be a really great complement to the hydrological information that we get from the resistivity system. When you think to things like unstable slopes, landslides, if we can have a good understanding of the hydrology and mechanics, we start to have a really good idea of the two main processes that are going to cause future failures. So that brings me to my final slide. I think the thing that I really want to hammer home with this is that it's a real step change in terms of how we can actually be proactive about monitoring these assets. So what I don't want you to take away from this is the idea that every embankment in the UK should have a prime system on it. That's absolutely not the case. This particular location has got the right sort of level of risk and cost associated with it, but having this very detailed monitoring system makes sense and it provides a lot of benefit in terms of the economics and the safety it brings. But it does also show that we don't need those very expensive systems. We can just use quite standard techniques through geophysics. You know, the first part I showed where we had those risk maps and areas that were showing potential future locations, it's still very powerful being able to understand where we need to target our sort of observations and remediations in the future. And that's a very quick, non-intrusive way of being able to get that data. Having the monitoring, though, means that we can understand our known risks better. So where we've had previous failures and repaired those, we can be proactive about making sure that they're still serviceable and performing the job. But also allows us to identify those unknown risks where we may have new leakage, and overall that contributes to the ongoing resilience of the embankments. Those early improvements, early repairs are 10 times less expensive, so that's a huge benefit to being able to continue to maintain this asset for the long term, so there's a big sustainability element there as well. And of course, having those repairs is much lower impact in terms of the environmental and also social impacts. We don't have to close those footpaths, we don't have to get environmental permits when the overwintering birds are there. So there's a very large sustainable element around that as well. So with that, I do just want to say thanks to all of my colleagues, both at AtkinsRéalis, at the Environment Agency, and also in the British Geological Survey. And if anybody has any questions, I'm very happy to answer them. Or if afterwards you have any questions, you want to get in touch with me through LinkedIn or my email address, then please don't hesitate to reach out. But thank you very much.
Thank you. Thank you. So, it's brilliant what you've been talking about. It's very close to Exeter.
Yes.
So, any question from our audience or any people online? Any question? We have time for 1 or 2 quick questions.
What's the sort of kind of next step? Is it always going to be sort of just adding mortar when you see that there's a failure? Is there sort of any future? Are you going to use it to potentially do something else with the embankment, or is it literally just sort of trying to prevent it from failing?
Yeah, the next step at the moment is while the Environment Agency look at future options for what they can do there, is to make sure that old asset is doing the best it can, basically.
Yeah.
That is the overarching goal. The things we're interested in, how we can develop the systems to make that better, easier to achieve. We want to really, so a lot of the insight from the system comes because we have people like myself who understand geophysical data and can translate that to someone who's got to manage the asset. We're really interested in looking at things like how AI might be able to help with those large data sets, because 26 data sets a day, a year's worth of monitoring, it goes on for another 10 years, it's a huge data set. So we've got to get better at how we can manage that and how we can pull the insight out. So that's a package of work we're looking at the moment, how we can integrate that into basically an easy to use dashboard that unlocks the insight for an end user who doesn't have this specialism. Yeah, exactly.
Yeah, also wondering, like, maybe given the fact that climate changes are hitting obviously harder and harder on any assets, like, is the Environment Agency thinking about changing approach, how they're gonna repair something, like a better way,
Yeah, so actually there's a step change in the environment which is being driven by DEFRA at the moment, which is an asset transformation program that is specifically trying to use this kind of monitoring data and that early insight to be more proactive rather than have things like emergency budgets where you can only repair things after there's a failure. They're definitely trying to move towards that. How can we spot things early and actually repair things early and prevent them getting to failure, which is a huge benefit.
Yeah, because currently I know they can't do much on emergency budget. That's the problem.
Yeah, but it's a ubiquitous problem. It's the same if I talk to Network Rail or anyone who's got long linear assets. It's a huge problem.
Yeah.
You can't. Nobody wants to wait for failures to happen.
And also, is there interest of because train tracks are very close? So is there interest from them?
Yes. Yeah, they are keen for us to keep that safe for sure. Yes, there is interest. Definitely.
I'm just wondering, you demonstrate this, you use those monitoring information to detect when there could be some failure.
Mm-hmm.
Could this be even more proactive, try to predict where it could happen?
Yeah, and that's what we're working towards at the moment. So the main outputs, so the full story was that the deliverable we were going to make from this monitoring system was like a quarterly report. And we realised very quickly that actually, when you have a near real-time system, writing a report every 3 months is just not agile enough to actually fit the demands of the system, the demands of the end user. And that's where this work now in sort of developing these accessible dashboards is so that we can actually get someone who's not a specialist to log in and say, okay, the data is telling us that here we've seen this decline in resistivity for a week, a month, and that indicates that something is changing here. Not the same as where we're seeing on other sections of the embankment where we maybe have repairs or where we've got no historic failure. We need to now go and see that in person to see if there's any indication and then maybe do something about it. So that is the predictive element is very much the next step.
Great, excellent. So I'm aware of time, we need to evacuate the room. So sorry about it. So thank you very much for this brilliant talk, and so hopefully we will hear more from you for further work. I know we can also work on this collaboration. Thank you very much. Thank you who participated online. Thank you.
Thank you.
Thank you.